Hey class, it's Mr. Hofstad here with the third lesson of our last unit on nuclear theory. And this lesson is nice and short, and it picks off nicely where we left off talking about our decay reactions. Because as our elements, as our atoms are decaying, they are emitting alpha particles, beta particles, gamma particles. And the rate that they're doing that is pretty important, right? We want to know how many of these particles are being emitted and therefore how much of our atom is decaying. So radioactivity, we've all heard this word often, is the rate of these radioactive emissions. So how many of these are being emitted each second, right? Emissions per second is kind of our general way of looking at radioactivity. So these are becquerels. They are one emission of any type. It's not specific to gamma rays or alpha or beta particles. It's just an emission of a particle each second. So if we're emitting 10 of these each second, we're going to have 10 becquerels. And these are all measured using a Geiger counter. And if you've checked out the Chernobyl documentary on HBO yet, you will have heard that device come up quite a bit. So radioactivity, how many emissions of these particles, right? These decay reaction particles per second. Madame Curie, might have heard of her if you've watched Big Bang Theory or if you've just looked into any physics in the more recent timeline, discovered that unlike any other reaction, radioactivity is not affected by temperature, pressure, bonding with other atoms. Right? It's a very stand-alone type of reaction. So radioactivity is not affected by things that other chemical reactions are affected by. There's only two different factors, and these are really important. Only two factors that will affect radioactivity is the mass of the sample, so how much of this atom or this sample we're looking at. So when there's more of it, it's more radioactive. We're going to have more emissions per second, having more of these unstable atoms. That should make sense. And the second part is what we're focusing on today, the half-life of this radioisotope. So radioisotope is kind of a new word. It's just broken. If we break it into two things, it's a radioactive isotope, right? The name kind of says it all. It's an unstable isotope of our element. And each element will have a different half-life. So a half-life, let's get into this. Half-life, we're going to look at using this capital T, half, as kind of our abbreviation, the variable for it. So capital T like with period, right? And it's half of its life, essentially. So it's the time required for half of our atoms, so half of our mass, to decay. Right? And when they decay, they're transmuting into different atoms. They're either gaining protons, losing protons, right? But they're changing from one atom to another atom as they're emitting and going through this decay reaction that we focused on last lesson. So every radioisotope has unique half-life. So not just specific to each element, right? Because we could have thorium-234, or maybe we have thorium-236. Those are different radioisotopes, they'll have different half-lives. So each specific radioisotope will have its specific half-life. Okay, let's look at this example and kind of get into the math behind this. So if we have this thorium-234, with a half-life of 24 days, that means that every 24 days, we are left with half the atoms that we started with. So we have 100%, we could even call that 100 grams if we wanted to look at it with mass rather than percent, because all of these things are really related. Half-life can be based on mass, it can be based on percentage of our start, it can be based on our emissions per second, our becquerels, because those are going to change as we have less mass. We know that from Madame Curie's discovery. So if we're starting with 100 grams, 100% of our thorium-234, after 24 days, right, that's our half-life. That means we have half of our original sample. So we now have 50 grams of these transmuted other atoms and 50 grams of our original radioisotope thorium-234. And if we go another half-life, right, we've split this into half, right? So we're looking at this. This is our new starting amount. And if we go another half-life, we're now at 25 grams, right? And if you went another 24 days, right, we can kind of continue this just by steps. Another 24 days, day 72, we would have 12.5 grams. So nice and neat, nice and exponential. I was about to say linear, but no, we have this exponential decay. So at 100%, right, that's the percent of the sample we have. You can change this graph to have mass. You can have it in our becquerels, right? There's different ways to analyze our half-life, but all of them will have this same exponential decay, where you're going to have this really steep part at the beginning, where we're going to decay to 50% in our first 24 days, right? We can see that these are all matched up. We have 100% with 0 time in days. So that's our start. Here's our day 24. We're at half of it. Day 48, we are now at 25%. And if we keep going in these intervals, look at 72, we should have 12.5, right? Then we go to 96, and we've got, what would that be, 6.25, so on and so forth. So you can kind of see too that you'll never have none of it, right? We have this asymptote on our x-axis, so it'll never quite reach 0 mass, but we'll get these really infinitesimally small amounts eventually. Okay, now time for the math. These are our formulas given on our formula sheet under our quantum mechanics. Oh, are they not? No, they're under atomic physics, sorry. So we're given this guy here, but unfortunately we're not given the n value. So that one becomes important for us to kind of memorize and understand. So we have this given. So again, we're using our naught notation, and naught is the starting amount at time 0. Right, amount at time 0 is another way you can think about it. So our final amount is equal to our starting amount times half, because we're looking at the half-lives, times n, the number of half-lives. So how many times have we cut in half? Here, this would be 1 half-life, 2 half-lives. So if we're going to calculate that, right, if we're looking for the final amount after our third half-life, we would take our 100, whether it's grams or percent, doesn't matter, 100%, because this amount can be mass, it can be our radioactivity in becquerels, it can be percent. Different questions will give you different things, but they will all work in this half-life calculation. So we start with 100, that's our n naught. We're going to multiply it by half of with an exponent of the number of half-lives. So if we're just double checking that our math works out, this is our second half-life, and we throw that in the calculator and we get 25. All right, so number of half-lives, this isn't given, but it kind of makes sense. The number of times you've split in half is going to be the total time that has been elapsed. So here we would have 48 divided by the half-life, which is 24. So at a total time of 48 days, we've undergone 2 half-lives. We've split our starting amount in half twice. This is a nice thing to keep in mind, right? They need to have the same units. Sometimes it'll be in days, sometimes it'll be hours, sometimes it'll be seconds. Just make sure that you're working with the same units, because obviously you want the time to cancel out top and bottom, so you're left with this number of half-lives, right? Just a nice reminder at how important keeping track of units and unit cancellation is in physics. All right, so that's all I got for you, other than this example that will be posted separately. Mr. Holloway went through it and explained nicely the two kind of methods. The first one would be just guess and check, kind of using this logical approach and our graph to estimate the number of half-lives, right? And plug and chug our estimations, our guess and checks. And there's also a logarithmic approach. I know students always hate logs, but there is that option for you students who want a deeper understanding. For this course, though, it will almost always be enough just to use this guess and check method. So you won't have to do the logarithms. It can be helpful to check your answers, though. So if you're feeling like going for it, give that logarithmic method a try on some of these homework questions and kind of use it to double check your other way of sort of guessing and checking. All right, that's all I got for you. Short little section of notes today. Hopefully the homework goes good, and let me know as usual if you have any questions at all. All right, see you, class.